The content presented is offered through Statistical Hub. Your support sustains Statistical Hub's commitment to providing high-quality educational resources for free through its open course programs. Explore additional courses on the Statistical Hub platform at www.statisticalhub.com.
Hello everybody, welcome back to our channel Statistical Hub. In lecture 1 of Bayesian Inference, we have discussed some basic concepts of probability, like some definitions: what is classical probability, what is frequentist view of probability, axiomatic view of probability, and conditional probability. Okay, we have looked into these concepts, and in continuation to those things that we have discussed, now we will be discussing independence. Okay, like what are independence events, and then after that we will be discussing the concept that is written on the board: random variables and distribution functions. Okay, so let's just complete this last topic of probability theory, basic probability theory, and then we will move to this thing. Okay, so yeah, talking about independence, I like this color more. Okay, talking about independence. Okay, so we know that we always say that if I am having two events A and B, then these two events A and B are said to be statistically independent when the occurrence or non-occurrence of other event does not affect the other. Or you can say that when occurrence or non-occurrence of event, let's say B, of event B provides no information about whether event A has occurred or not. That's very simple definition: has occurred or not. Okay, so if B has occurred but it does not provide any information, it does not provide any evidence that A will also occur. So basically we mean to say that when we are talking about the conditional probability, that probability of A given B, which is probability of occurrence of A when B has already happened. Now we are saying that when these two are independent events, the probability that of occurrence of A would not be determined or would not be dependent on the probability of occurrence of B. So this thing would be equal to probability of A because they are independent. Or you can say similarly that probability of A would be equal to probability of A given B naught. Like this is corresponding to happening of the event B, and this is corresponding to non-occurrence or non-happening of the event B. Okay, so they are not dependent on each other. So whether we are finding out the probability of the event A for non-happening of the event B, that would be probability of A, because we are saying that A and B are independent. Okay, so if A and B are independent, then we can take any complements like A bar and B. Okay, A B bar and simultaneously A bar B bar, they would also be independent if my if my events A and B are independent. Okay, now in the independence there is a very important property that you must notice, that is that if you are having probability of A which is not equal to 0, okay, probability of B which is not equal to 0, then the events A and B cannot be simultaneously mutually exclusive and independent. Okay, there are two things that I am saying, that if you are having two events A and B, then these two properties can't happen simultaneously. If the events are mutually exclusive, then they cannot be independent, and if they are independent, then they cannot be mutually exclusive. Okay, let's see how. Okay, to see this, let's just consider first scenario. Okay, we are saying that let A and B are my two events which are mutually exclusive. Mutually exclusive. Now what is the condition that I am considering? That probability of A or probability of B, neither of their probability is 0. Okay, so basically we are considering that probability of A is greater than 0 and probability of B is greater than 0. So if they are mutually exclusive, then this means that the intersection of these events would be equal to 5. Okay, and the probability of A intersection B would be equal to 0. Okay, now let's write this probability of A intersection B into the format of multiplication theorem of probability. Okay, that I can write this probability of A intersection B as probability of A into probability of B given A, or you can also write it like probability of B into probability of A given B. Now we know that the probability of A cannot be equal to 0, right? We have just seen this condition where we are putting this condition firstly, and simultaneously that the probability of B cannot be equal to 0. But this is saying that the probability of A intersection B is equal to 0. So this thing is also equal to 0, this is also equals to 0. But this term can't be equal to 0, this term can't be equal to 0. So from this implication we are concluding that probability of B given A is coming out to be 0, and from this probability of A given B is coming out to be 0. But for the independence, we have just seen that if I want A and B to be independent, then the case has to be probability of B given A has to be equal to probability of B. Okay, it should not depend on A, and simultaneously probability of A given B has to be equal to probability of A. But here they are coming out to be 0, and they are not equal to probability of B, and here it is not equal to probability of A. So from here you can say that two mutually disjoint events with positive probabilities are always dependent, or you can say that they are not independent. Understood? Okay, now let's see the second scenario where we are going to consider that my A and B are independent events. Okay, so let A and B are independent events. Now the same thing, they can't be equal to 0, so probability of A is greater than 0 and probability of B is also greater than 0. Okay, so if we are considering that they are independent, then this means that the probability of A intersection B would be equal to probability of A into probability of B. Right? How can we say this? You can say it here. Okay, because see it here. Whenever you are saying probability of A given B is equal to probability of A. Right? Now expand this thing. That is probability of A intersection B upon probability of B, which is equal to probability of A. So from this we are getting the result that the probability of A intersection B is equal to probability of A into probability of B. So if this condition satisfied, that the simultaneous occurrence of two events, the probability of simultaneous occurrence of two events is equal to the multiplication of their individual occurrence, then they are independent. Okay, so that's the condition for two independent events. Okay, when we are saying that the A and B are independent, then they needs to satisfy this condition, right? But for mutually exclusive, what is the requirement? For mutually exclusive, I should have the probability of A intersection B is equals to 0. Okay, but this is not the case here. They can't be equal to 0 because they are independent. So from here we can conclude that A and B cannot be mutually exclusive. Exclusive. So you can say that two independent events can't be mutually exclusive. Mutually exclusive. Got my point? Okay. Now let's come to the thing, which is, I'm again mentioning this term again and again. What is mutually independent? Okay, we are mentioning this term mutually exclusive. That means that they are having nothing in common, or the simultaneous occurrence of them is cannot occur. Okay, but there is one more thing. We have just discussed the term independence, but now the next thing is, what is mutually independent? Let's change the color. Yup. Mutually independent events. So for the mutually independent events, let's just say we are having some events like A1, A2 to AN. I am having n events. Okay? And we would say that these n events are mutually exclusive. Okay, these n events, which are defined on some sample space basically, then these n events would be mutually exclusive if they are independent in pairs. Okay, I think I have said mutually exclusive, but I mean to say mutually independent. Okay, yeah, so these n events are mutually independent if they are independent in pairs, triplets, quadrats, like going on, etc. Okay, so yes, if they are independent in all these scenarios, like taking two pairs at a time, taking three pairs, taking four pairs, taking five at a time, okay, like similarly going on like this, then if they are independent in all these conditions, then we will say that my function is mutually independent. For understanding this case, let's just consider a very simple thing. I am considering three events, A1, A2, A3. Okay, now there is two things that we usually hear. One thing is pairwise independent, and the other thing is mutually independent. Okay, so mutually independent and the pairwise independent. Pairwise independent means that if I'm taking the pairs of these events, probability of A1 intersection A2, A2 intersection A3, probability of A3 intersection A1. If they are coming out to be probability of A1, probability of A2, probability of A2, probability of A3, probability of A3, probability of A1. If these three conditions are satisfied for these three events, then I would say that I am having pairwise independent events. Okay, pairwise independent events. But for mutually exclusive, in addition to these three conditions, you need to check one more condition, that is probability of A1 intersection A2. Let me write it in on another page. Probability of A1 intersection A2 intersection A3 has to be equal to probability of A1, probability of A2, probability of A3. Okay, and those two conditions also, like probability of A1 intersection A2, probability of A2 intersection A1, and probability of A1 intersection A3. So if these four conditions are satisfied, then we would say that the events are mutually exclusive. And if those three conditions that we noted on the previous page, if those are satisfied, then we would say that the events are pairwise independent. Okay, mutually independent. Okay, Now yes, this is the scenario for pairwise and mutually independent. Okay. Now let's come to the very next thing. So if you increase your number of events, then the conditions for the mutually independent events that you need to check would also increase, right? It's very simple. So it depends like how many conditions you would need to check. Okay. So if you are having n events, a1 a2 to n events, and you are checking mutually independent events, whether they are mutually independent. So firstly you will check in the pairs. Okay, you will check that the probability of ai intersection aj has to be equal to probability of ai into probability of aj. Then you will check in the triplets, probability of ai intersection aj intersection ak. Okay, that has to be equal to the individual probability of them. Then you will check on quadruples, and then you will keep on doing this until you will take all the terms at one time. Okay, like a1 intersection a2 to intersection an, that is just the multiplication of all these terms. Okay, so how many conditions you will be forming? Okay, here you are actually taking total number of conditions. So if you take total number of conditions that you need to check, so I am having n events, taking two pairs at a time, I can use a combination, right? So from the total of n events we can take two pairs at a time. So what will be the total cases in this particular cases when I am taking pairs? That will be nc2. From total of n events we are taking 3 events at a time, that will be nc3. Similarly going on, we will continue this process till we take n events at a time, so ncn. Okay, now we can make the formula from this. Okay, that is I can subtract and add, like let me do it in another step. I can do it nc0 plus nc1 plus nc2 going on till ncn, and simultaneously subtracting these two, nc0 minus nc1. Okay, which is this formula is just the binomial theorem. So I can say that this is 2 raised to the power n, like 1 plus 1 to the power n minus 1 minus n. So these are the total number of conditions that we need to check for if you are having n events or any number of events. Okay, you can just put the, if you are having 3 events, you can just put the value of n is equal to 3, then you will get your result. Okay, so yeah, this was the case of independence. We have discussed independence in full detail. Now let's discuss the concept of random variable. Okay, as we will be discussing about the distribution. So the first, oh shit, yeah, so the first thing that we need to understand is random variable. Okay, so while defining a random variable, we say that we are having sample space S, which is the set of all possible outcome. This is my sample space. Now random variable is just, you can consider it is like based on the theory of functions and set theory. If you know these two concepts, then you will understand the random variables very well. Okay, set theory is basically not is not in the definition of it, but yeah, it will be used in while you are calculating the probability corresponding to certain events. Okay, so yeah, talking about the random variable, just like the functions, what do we do in the function? That we say that I am defining any function f which is defined on some domain to some range, right? That we say in the function. Similarly, we are doing this in the random variable. So we are saying that I am having some random variable x which is defined on some domain to some range. Okay, now the main thing is what is the domain and what is the range of these random variable, like how am I doing the mapping? That's the main thing. So what are we doing? We associate a real number with each outcome of an experiment. we are doing one-on-one mapping on whatever be the possible outcome, whatever the outcome is occurring on my in my experiment. Okay, so we are doing the mapping from sample space to the real number. Okay, we are doing one and only, we are assigning one and only one real number to one particular outcome. Easy. So sample space is my domain and my range is the set of real numbers. It is the set of real numbers. Okay, that is my random variable. Now let's take an example. When you are okay, the easiest example ever that you have heard even thousands of times, that when you are tossing a coin. Okay, when you are tossing a coin, what is your sample space? We will be having head and tail. And if you are defining your random variable x of w, let's say, which is equal to 1, when you are getting a head, and you are defining a random variable 0 when you are getting a tail, then actually you are assigning a value 1 when your outcome is head, and you are assigning a value 0 when your outcome is tail. Okay, so that is the mapping, and your domain is head and tail, that is sample space, and your range here is 0 and 1. Like that's what you are doing the mapping. So here x is equal to 0 comma 1. Okay, and if you guys remember, then this random variable x of w is a particular case of random variable which is very important, Bernoulli random variable. We will be discussing Bernoulli distributions. Yeah, so this is a Bernoulli random variable. Clear? Okay, now let's talk about the distribution. We have defined the random variable. I am sweating so much, I don't know why. Yes, so yeah, now let's talk about the distribution functions. Okay, distribution functions. So talking about the distribution functions, or you can say cumulative distribution functions. Cumulative distribution functions. Okay, so cumulative distribution function is basically defined as a real valued function which is right continuous, a real valued function f of x, okay, which is defined on some domain and some range. Okay, just like the random variable, there is a function, a real valued function f of x, which is defined on some domain to some range. Okay, now the function is defined as probability x less than equal to x, where the range of x is from minus infinity to infinity. Okay, so your domain is basically minus infinity to infinity, and your range is, as it is a probability, so probability always lies between 0 to 1, so the range would be 0 to 1, right? And we are saying, if you are seeing this in a continuous, this is for discrete case. Okay, if you are seeing this in a continuous case, then you are actually writing it like f of x is equals to minus infinity to x for f of x into dx, where f of x is the probability density function. Okay, now let's discuss some properties corresponding to it, that if your function f is absolutely continuous, then you can find out the probability density function. Okay, by differentiating the distribution function, that is f dash x, which is d by dx of f of x, gives you the probability density function which will be greater than equal to 0. Okay, which will be greater than equal to 0, that is your distribution function. Okay, now other property, that when you are having the range of x as from minus infinity to infinity, so we are seeing that what is the case of f of minus infinity, extreme bounds, and what will be the behavior of f at infinity. That is, you are just seeing the limiting behavior, that limit x tends to minus infinity of f of x, and what is limit x tends to infinity of f of x. Okay, now you can see it. we have said that this is a right continuous function. Right continuous function. Okay. And the function is basically probability x less than is equals to x. Okay. So when I am saying that limit x tends to minus infinity. Okay. We are talking about limit x tend to minus infinity, that is probability x less than equal to x. So a probability of a function lesser than minus infinity would be 0. Very basic. Okay. And limit of a function x tends to infinity of this thing x less than equal to x, where x is actually x is tending to infinity. That means I am considering the whole area. You can consider it like this, any graph. Okay. So this is tending to infinity and this side is tending to minus infinity. Okay. So any area like lesser than this portion, that means whole area. Okay. And lesser than this portion, that means only this area. Okay. Which will be the probability of, like, it will be minus infinity and lesser, so there will be no area absolutely. But yeah, considering all the area, so here we will be having probability of this would be 1. Okay. So 1 and 0. Okay. So this is the distribution function. And talking about the random variable, we are having two types of random variable. The one is the discrete case and the second is the continuous case. Okay, that is discrete random variable and the second one is the continuous random variable. Okay, so in the discrete random variable, we are talking about a countable number of real numbers. Whenever my random variable is taking a countable number of real values, then it is a discrete random variable. And a continuous random variable is when it can take all real values under a certain limit. Okay, like minus infinity to infinity, 0 to 1. Okay, it can take all real values. Then it is a continuous random variable. Okay, so we will be discussing all the cases, like whether it is a cumulative distribution function, whether it is a density function or mass function. We will be discussing on both of these cases. Okay, so yeah, we have already discussed the distribution function, which is on like how to calculate it on the continuous cases, and you can use this while you are calculating for the discrete cases. Okay, this is just the expansion. So yeah, let's now talk about the probability mass function. Okay, probability mass function. So when probability mass function is actually a point probability for a discrete random variable. When you are having a discrete random variable, then finding out the point probability at a certain point, probability x is equals to x, that is equal to some probability pi, for like probability of x is equals to x, let's say p. Okay, that is your point probability. Okay, similarly, if your x is random variable is taking some values like x1, x2 to xn, then you are assigning different probability, not assigning, you are finding the different probabilities corresponding to each random variable, that is xi is equal to pi. Then the very basic thing, that probability of each of these random variable would be greater than equal to 0, and if your random variable is taking n values, then the sum of probabilities of all these random variable would be equal to 1. Similarly, in the continuous cases, we assign the probability, like we find out the probability density function. Okay, when your x is a continuous random variable. Okay, so in this case, we say that my function f of x is the probability of a random variable x when it is lying in under certain range. Okay, so here x is, for the continuous function, we say that x is lying between from minus infinity to infinity. Now a function is said to be the probability density function if it satisfies certain properties. Very first thing, that f of x is greater than equal to 0 when you are calculating the f of x under a certain range. And second thing, that from minus infinity to infinity, f of x dx is equal to 1. That is, the area under the consideration, or you can say the total probability, has to be equal to 1. Okay. Next thing, when you are calculating the probability under a certain event e, where an event e you can say is between a to b. Okay, A to B. Then you can calculate the probability from A to B by using A to B f of x into dx. Okay, so this is probability density function while we are having continuous random variable, and this is probability mass function for discrete random variable. Okay, so till now we have discussed the random variable, only one dimensional random variable. Okay, now let's move to the probabilities and the distribution functions where we will be having two dimensional random variables. That will be an interesting case. Okay, so two-dimensional random variable. So talking about the two-dimensional random variable, we will be having x and y, which are two random variables. Okay, two random variables which are defined on some sample space S. Okay, now again same thing. If I am having two random variable x and y, then there will be some certain function which is defined on some domain to some range. So the domain would be sample space S, and the range would be now r square. That means r square. Why? Because I am having two random variables, so I will be considering all the pairs of those random variables. So that will be, the pairs would map to the two-dimensional thing, that is r square. Okay, r is here real number, so r square, two-dimensional random variable. Okay, so function would assign the points to the r square. Now let's consider the joint PMF. What would be the joint PMF in this case? So that is Pxy x comma y would be equal to probability x is equals to x comma y is equal to y. That is the joint PMF of two random variables, and we already know that the sum of probability in this case also has to be equal to 1. Sum of probability has to be equal to 1. Okay, now the next thing, if I am having the joint distribution, joint PMF of two random variables, now I would be curious about how to find out the marginal from it. Okay, so from these, how would you find out the marginal PMF? Marginal probability mass function. That is what? How would you find out probability xx, or how would you find out probability y of y? Okay, so probability x of x means, that means probability x is equals to x. Okay, so if you put all the values of the random variable corresponding to y, then you will get the marginal probability mass function for x. That means you are going to put probability x is equals to x comma y is equals to yi. Okay, let's use the summation here. Yes, summation I is equals to 1 to infinity. Okay, so I am putting all the values corresponding to y. Whatever the random variable y is taking, y must be taking the values. Y random variable is taking the values y1, y2 like this, and x random variable is taking the values x1, x2 like this. So I am putting all the values corresponding to y random variables, then finding out the probability. Then this is denoted by pi dot. Okay, that means I will get my marginal. Simultaneously, if I am finding out the probability marginal for the y, I will put all the values corresponding to the x. Okay, all the values of the random variable corresponding to x. That is j is equals to 1 to infinity for probability x is equals to x of j, y is equals to y. Okay, that will be p dot j. Okay, so that's what happening here. Now if you add these probabilities, okay, from this you are getting the marginal, that is this thing, and from this you are getting the marginal, that is this thing. Okay, so you can find out the PMF and marginal is like this. Now similarly, you can do the same thing for the for continuous cases. Okay, let's see how. Yes, okay, so basically when we are calculating marginal, okay, let's write down in one format. Okay, so when you are calculating marginals fxx, okay, In the discrete case, you are writing summation y pxy x comma y. That means you are putting all the values corresponding to y. Okay, when you are finding the marginal of x. And when you are finding the margin of case in the discrete case, okay, in the discrete case, this is for the discrete case. And when you are finding it for the continuous case, then you will be doing minus infinity to infinity f of x comma y into dy. That means integrating with respect to y. Finding the marginal for x, integrate with respect to y or put the values of y. Similarly, when you are finding out the marginal corresponding to y, then you will do the same thing, that put the values of x in the discrete case, or in the continuous case integrate with respect to x. Then you will get the marginal for the y. This is for continuous and this is for the discrete case. Okay, understood? Okay, now similarly when we are saying these are corresponding to joint PMF, marginal PMF. Similarly, we have talked about joint PDF. F of x comma y is my joint PDF, and from this joint PDF we have find it out our marginal PDF, that are fxx and fyy. These are my marginal PDFs. Okay, yes. Now let's come to the next thing, which is two-dimensional distribution function. Okay, now just like the one-dimensional distribution function, if we discuss two-dimensional distribution function, it would be same thing but in two dimension distribution function. So if we are talking about fxy x comma y, that would be equal to probability x less than equal to x comma y less than equal to y for y for x comma y belongs to r square. Okay, this is for discrete, and if you are calculating for, similarly you will just put the integration when you are doing it for the continuous cases, that is minus infinity to y minus infinity to x f of x comma y dy dx. And same like the previous cases, I will be having f of x comma y, which is non-decreasing and continuous on right. Okay, and the next thing, that f of infinity comma infinity, that would be equal to 1, just like I have discussed in the for one dimensional, and the f of x comma minus infinity is equal to 0 for all x, and f of minus infinity comma y would be 0 for all y. Okay, you can check these with the help of limit. Okay, next thing, you can find out the joint PDF with the help of joint CDF. Okay, joint distribution function, by differentiating it two times f of x comma y del x del y, then you will be getting f of x comma y, which is joint PDF. Okay, yes. So this is all about the two-dimensional distribution function. Okay, similarly you will be having conditional PMF. Okay, so when you are talking about the conditional PMF, okay, now what is conditional PMF? Conditional PMF is basically probability x is equals to xi given that y is equal to yj. Now just like we open the probabilities in the conditional probability, it is similar to that. So that is probability x is equals to xi intersection y is equals to yj upon probability y is equals to yj. This is conditional PMF. Similarly, you will be having conditional PDF. Okay, where I am considering that f is my PDF of two-dimensional random variable. Okay, then f of y given x would be equal to joint of those two random variables upon marginal of x. Okay, for f of x greater than 0, because we don't want denominator to be 0, otherwise the function would be infinity. Similarly, you can write it down for the conditional PDF of x given y, that would be equal to f of xy x comma y, the joint of these things upon f of y. Okay, and this is the these are the conditional PDF. Okay, and simultaneously, if we are talking about whenever where in this case, how would you say that x and y are independent? Then if you are having x and y are independent, then in that case your fxy x comma y would be equal to fxx into fyy. Okay, just like we have discussed the independence in the probability case, the same scenario follows here, that if you are having two x and y random variables, they are independent, then x and y are independent random variables. Okay, then you can write down the joint probability into the product of the joint distribution into the is equal to the marginal distribution, multiplication of the marginal distribution. Okay, so this was about all the concepts that we are going to use: two-dimensional distribution, how to find out the joint from the marginal, conditional PMF, conditional PDF, all these things. Okay, now in the next lecture we will be discussing we have discussed basically distribution function, probability mass function, probability density function for one dimensional and for the two dimensional. Now we will be discussing, there is one more important thing, that is what is truncated distribution. Truncated distribution. Okay, truncated distribution, what is this concept of truncated distribution? Then after this concept we will be discussing some basic properties, like how to, like what is conditional expectation, all these concepts. Then we will come to the main concept. These are all the basic concepts that we are covering right now till now. Okay, then after this we will be discussing Bayesian framework. Okay, that how does this framework is applicable and how will we use it. Okay, Bayes theorem and all these concepts. So yeah, that's all about for this today's lecture. We have discussed the random variable and the distribution function for one dimensional random variable and two dimensional random variable. Now the truncated distribution and the expectation part, we will be discussing them in the next lecture. Okay, so stay tuned for the lectures that we will be covering. Okay, so yeah, all the best for your learning. Bye.